So certainly one of the two best known equations in all of physics has to be Newton's second law. So ask almost anybody who's taken a science class and they'll be able to tell you that Newton's second law is F equals ma. But just like we discussed with Newton's first law, our common version of Newton's second law is missing some pretty important details. And in this case, those details are really in the notation. So it's still F equals ma, but notice there's a sigma out front because we're talking about a summation, and then both F and A, the force and the acceleration, are vectors. So the correct way to think about Newton's second law is that the net force as a vector is equal to mass times the acceleration vector. So what does this tell us? Well, for starters, it says that if an object is in equilibrium, so being in equilibrium means that when you add up all your forces as vectors, they cancel out. So you have a balanced net force. So the magnitude of your net force is 0, which means the acceleration is 0. Which is why in equilibrium, we said that objects remain at rest or continue to move in a straight line at a constant speed. However, if your object is not in equilibrium, then you have an unbalanced net force. So you've added up all your forces acting on your object, you've added them up as vectors, and you've gotten an answer that's not 0. What that means then is since you have a non-zero net force, you have to have a non-zero acceleration. So unbalanced net forces cause objects to accelerate, and Newton's second law quantifies what that relationship is. It says that your unbalanced net force is equal to mass times the value of that acceleration. So again, reading what this equation tells us is a couple critical points to keep in mind. The first one is that the net force and the acceleration as vectors always point in the same direction because mass is always a positive quantity. And the thing, again, the critical word here, just to overemphasize it, is always. We're going to take advantage of this in working Newton's second law problems because in many cases we'll be able to figure out what the direction of the acceleration is, and knowing the direction of the acceleration is going to help us find the preferred coordinate system for doing the vector addition. The other thing that's interesting about Newton's second law is that it gives us a new definition for mass. Mass is a measure of an object's resistance to being accelerated. This is known as the inertial property of mass. Mostly what this says is that if you have the same net force act on a small mass object and a large mass object, that the larger the mass is, the smaller the resulting acceleration is going to be. So bigger masses are more resistant to being accelerated, right? That's the inertial property of mass. The last critical thing to recognize about Newton's second law is, of course, that it is a vector addition problem. So fundamentally, Newton's second law says we're going to take all the forces on the left-hand side of the equation, we're going to add them up as vectors. Typically in this class, because we work most of our problems in 2 dimensions, that means that this is going to be, we're setting up component equations for x components and y components. We're going to set up one equation per coordinate axis. So again, if you've got just things, all your forces are aligned horizontally, then maybe you just set up a single equation and label it x. If you have all your forces are aligned vertically, then again, you just need a single equation and maybe you label it y. If, on the other hand, you've got things that act both horizontally and vertically, we're going to need to break those up into their horizontal and vertical components and set up 2 component equations. Now, breaking up the force vectors, we tend to be pretty good at. But again, what Newton's second law is telling us is that you not only need to break up the force vectors, you also need to break up the acceleration vector into its components. So the sum of the forces in x, the x component of the net force, is equal to mass times the x component of the acceleration. And the sum of the forces in y is equal to mass times the y component of the acceleration. So it's really critical when working Newton's second law problems to recognize that not only do we need to break up the forces into their x and y components, we also need to break up the acceleration vector into its x and y components.